Hello, my dear students. Welcome back to SHLOKA'S Academy YouTube channel. In last session, we have discussed about isotherms. That means we have done with isotopes, isotones, isobars, isodiaphers, and isoelectronic species. And in today's class, we are going to discuss about the dual nature of electromagnetic radiation. That means, like light, the electromagnetic radiations also possess dual nature. Dual nature means here we have two natures. One is wave nature and another one is particle nature. In today's class, we are going to discuss about wave nature of the electromagnetic radiation. Wave nature of the electromagnetic radiation, right? Wave nature of electromagnetic radiation. First of all, what are electromagnetic radiation and how could be electromagnetic radiations generated? What are the properties that are being associated with electromagnetic radiation? One by one, we will discuss in this video. First, so let me discuss what is electromagnetic radiation. I am abbreviating it as EMR. How do these electromagnetic radiation can be generated? It is very simple. If I take a magnet, if magnet is oscillating in presence of an electric field, then it produces electromagnetic radiation. Or if an electric charge is oscillating in presence of a magnetic field, then also that can produce electromagnetic radiation. See here. So in this wave nature of electrode, first the scientist James Maxwell, who suggested that electrically charged particle, what I said, a charged particle, right, moves under acceleration, alternating electric field and magnetic fields are produced and transmitted. Means those radiations which can be produced by either oscillation of an electric charge in a magnetic field or by oscillation of a magnet in an electric field. And these fields are transmitted in the form of waves called electromagnetic waves. Here we are going to discuss about wave nature of electromagnetic radiation. That is why I can say that these field means whatever the electromagnetic radiations that are being produced by this oscillation can transform in the form of waves, which are called as electromagnetic waves or electromagnetic radiations. Right. And James Maxwell was the first scientist to reveal that light waves are associated with oscillating electric and magnetic field. Means whatever the electromagnetic radiations coming out from the oscillation of an electric charged particle in magnetic field or oscillation of a magnet in an electric field which are coming out, so they may possess both light and as well as wave, right? So now electric, and they are also possessing electric and magnetic field. How these are possessed means I'll explain. The electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and are also perpendicular to propagation of wave. In the next slide, I will explain with the diagram how they are. And these electromagnetic radiation, whatever the electromagnetic radiations we have taken here, these electromagnetic radiation do not require any medium to propagate. For example, if you take sound waves, in order to transmit sound waves, they must require medium. Water waves also, they require medium. But when you take electromagnetic waves, they do not require any medium. So they can even move in vacuum also. So next, we will discuss how they are. Right. This is x-axis. What is this x-axis? That I can take it as a propagation of light, electromagnetic radiation. X-axis means the electromagnetic waves are traveling in this direction. This is right path of electromagnetic waves, path of electromagnetic radiations. In this direction they are traveling. Next, on y-axis, this is y-axis, right, and this is z-axis, right, and this is a plane perpendicular to the x-axis, and along this x-axis I can imagine that it is an electric field. What it is? It is an electric field, right? And here, which is called magnetic field. The green line is magnetic field, and this x-axis is the direction or propagation of waves. Now you just observe this x-axis, and one is along y-axis, and one is along z-axis. How these x and y-axis are perpendicular to each other, right? And z-axis is perpendicular to x and as well as y. Means all three, magnetic, electric, and propagation. These three are perpendicular to each other and are mutually perpendicular to each other. So this is every electromagnetic radiation that has been associated with both electric field and as well as magnetic field. And how they are associated means they are perpendicular to each other and are mutually perpendicular to the direction of propagation of wave, right? So next we will discuss about what are the properties, the characteristics of these properties, right? First, what is electromagnetic spectrum? We have to discuss a series of wavelengths of various color bands of visible region is called as spectrum, right? Let me take a series of wavelengths or various regions of electromagnetic radiation is called spectrum. For example, I have four radiations: 1, 2, 3, 4. Right. If I arrange these four radiations either in increasing order of their wavelength or in decreasing order of their frequency, then I can call it as spectrum. As the spectrum is arranged by, as the spectrum is arranged by electromagnetic radiations, I can call them as electromagnetic spectrum. Electromagnetic spectrum. A series of closely packed lines is called band. Very closely. So that we will discuss about band spectrum, all these things we will discuss. And here we have continuous spectrum. If all these four are arranged in a particular order, I can say that it is a continuous spectrum. Example, rainbow. In rainbow, if you take with GR, right, violet color merged into indigo, and indigo merged into blue, blue merged into green, green merged into yellow, yellow merged into orange, orange merged into red. And this is an example of continuous spectrum. And from this visible region, if I remove blue color and yellow color, then whatever the spectrum I will get, that is called as discontinuous spectrum. If any wavelength or color is missing from it, then it is called as discontinuous spectrum, right? So now frequency of values of EMR or electromagnetic radiations means what is electromagnetic spectrum? I will discuss. These are gamma rays. What are these? Gamma rays, right? And their frequency value is 10 to the power of 24 to 10 to the power of 22 and 10 to the power of 20, right? I can write all visible, IR, and all these, right? So this is what a perfect systematic arrangement of various electromagnetic radiations in the decreasing order on moving in this direction. What is the frequency of this one? 10 to the power of 24, and here only 10. Means on moving in this direction, the frequency mu value is decreasing. A systematic arrangement of various electromagnetic radiations in decreasing order of their frequencies is called as electromagnetic spectrum. Understood? And this is visible region. And if I go with next, that is VGR, visible spectrum. What are the violet, indigo, next blue, green, yellow, orange, and red. So this is, if I am moving in this direction, lambda value increasing and frequency value decreasing. The systematic arrangement of various, right, this is wavelength in nanometers, 400 to 750 nanometers. As I am moving in this direction, wavelength is going on increases. And what about frequency? Frequency will decrease. This is also various colors I have arranged in increasing order of their wavelength or decreasing order of frequency. So I can call it as a spectrum. As it is visible with the human eye, I can say that it is a visible spectrum. Next, we will discuss measurable characteristics of EMR. Means I said that electromagnetic radiations are associated with waves. That means that should be characterized by wave properties or not. What are the wave properties if I consider wavelength? The first wave property is wavelength. And how can you choose a wavelength? The distance between any two successive crests and any two successive troughs is called as wavelength. What is this? I will explain. This is a propagation of wave. Means along this x-axis, the wave is moving, right? And this is x-axis. This is y-axis, right? And this is z-axis, and this is electric field, crest, right? What is crest? This is called crest. This is called crest. And what is trough? This is called trough, right? This is crest, and again trough. This is trough, right? Trough. Now the distance between any two successive troughs are crest. This is the distance between two successive. Two successive means neighbors. Otherwise you can take these two also. So this distance is called as lambda or wavelength. Otherwise the distance between two successive troughs, this one, these two are successive, this is also lambda. So this is wavelength. How can you define? The distance between any two successive crests or troughs is called wavelength. So in the diagram you can clearly know that what is trough and what is crest. Understood, all of you? Now this is about the wavelength. Next, wavelength is measured in different units. Generally we can measure in angstrom unit, and 1 angstrom unit is equal to angstroms. 1 angstrom unit is equal, if you want to measure it in meters, that should be 10 to the power of minus 10 meters, or in centimeters 10 to the power of minus centimeters, minus 8 centimeters. These values are very important. You have to remember, because in the numericals most of the time they will give centimeters and we have to convert them into either nanometers or angstrom units. And I can also use picometers. 1 picometer is equal to 10 to the power of minus 12 meter, or 10 to the power of minus 10 centimeter. And I can also use 1 nanometer is equal to 10 angstrom units, or 1000 picometers, right? And I can also use 1 angstrom unit is equal to 100 picometers, right? 1 micrometer or 1 micron is equal to 10 to the power of minus 6 meters. Right, this is how we can use the wavelength in different. Next, frequency. What is frequency? Number of waves or vibrations or oscillations made by a wave in 1 second is called as frequency. Number of waves or vibrations or oscillations that could be done by a wave in 1 second is called as frequency. And it is denoted, the frequency is denoted by CPS. CPS means cycle per second, or hertz, right, or hertz. Next, 1 hertz is equal to how many? 1 CPS, right? And mu is equal to, actually the frequency is denoted with a symbol mu, and that is equal to C by lambda. And from this we can say that mu, that means mu is inversely proportional to lambda. Why? Because mu is equal to C by lambda. The C is speed of the light, which is always constant. If I remove this constant, I can write it as mu is inversely proportional to lambda, right? Next, mu is equal to frequency, and C is lambda is wavelength, and C is velocity of light, which is constant. So here this is. And what are the units? Per second. Example, here frequency of UV radiation is 10 to the power of 16 Hz. Right. Next, wave number. What is wave number? Number of waves present per unit length is called as wave number. It is denoted by mu bar, which is equal to reciprocal of 1 by lambda. Wave number C. This is mu bar, which is a reciprocal of 1 by lambda. And what are the units? Obviously, either centimeter inverse or meter inverse. Centimeter inverse or meter inverse. Wave number is the reciprocal of wavelength. Right. So now if I give what is the value of 300 nanometers in terms of angstrom, we know that 1 nanometer is equal to 10 angstrom units. Substitute. So it will be equal to 3000 angstrom unit. It is very simple question. There are options they are given, 4 options. So you can go with your 3000 angstrom units. The solution I have given here. Right? Understood all of you? So this is about today's session. In next session, we will discuss particle nature of the what is that electromagnetic radiation.